Hello, my name is Zhang. I'm from the Department of Chemical Engineering and Material Science at the University of Minnesota. What I'm going to present here is joint work with my former postdoc, Andrew Allman. It's about applying branch and price to a certain class of non-convex mixed integer nonlinear programs. This work was mainly motivated by the following observation. There are these two very important technologies in mixed integer optimization that have matured over the past 2 or 3 decades. One is global optimization of non-convex MINLPs, which has given us many of the solvers that we love, like Baron, Antigone, Skip, and others. The second is decomposition of huge mixed integer optimization problems using branch and price. However, on the one hand, the current global MILP solvers are still by far not as scalable as their linear counterparts. And on the other hand, branch and price has been applied to really large mixed integer optimization problems, but almost exclusively to MILPs. So this begs the question, can we somehow combine the strengths of the two to solve large, suitably structured non-convex MILPs? Surprisingly, this hasn't been done that much in the existing literature. At least we couldn't find much. The most relevant or most closely related works that we could find are those by Ivo Novak and co-workers, where they use column generation to generate inner and outer approximations of block-separable non-convex MILPs that also involve solving pricing problems that are easier in MILPs. What we're proposing is very much in the same spirit, but I would say our approach is probably much more straightforward. We didn't have to introduce any new theory whatsoever. In fact, if you're familiar with branch and price, it will probably be immediately clear how it works. So the class of MILPs that we consider in this work has the following general structure. So we have 3 sets of variables, x, y, and z. The objective function is linear in x and has a second part that's nonlinear in y and z. Then we have these linear complicating constraints that involve x and y, and the x variables can be both continuous and discrete. We call them complicating constraints because the assumption is that if we remove these constraints, then this entire problem becomes easier to solve. Then we'll have these y variables that are integer and bounded. We'll call them linking variables because they link the linear complicating constraints with the nonlinear subproblem constraints here. And the subproblem constraints here also involve the third set of variables z, which also can be continuous and discrete. Now I say that the assumption is that this problem becomes easy to solve if we remove the complicating constraints. This can have multiple reasons, but the most common one is that the subproblem has a decomposable structure. In that case, the problem would look like this, where this set script I here denotes the set of subproblems that we could solve independently once the complicating constraints are removed. And in our case, this essentially means that the subproblems are sufficiently small that we can use a global MILP solver to solve them. In fact, in all the examples that I will show, they have this decomposable structure, but for ease of notation, I will use the general structure to explain how the algorithm will work. Now, the first thing we need to do is to apply a Danzig-Wolf reformulation using a discretization approach. So consider this feasible set for the y variables, the script y, without considering the complicating variables. So what we have here are essentially just the problems or the constraints from the subproblems, and the set script y is just that feasible set of the subproblem projected onto the y space. In this illustrative 2-dimensional example here, we have y1 and y2. The points here, they denote integer solutions, and then the shaded area here is the feasible region without the integrality constraints. So you can see they can be nonlinear and non-convex because the subproblem constraints can be nonlinear and non-convex. So then the red points here, they constitute my set y, which is essentially just a set of finite discrete points, finite set of discrete points. Say we'll have capital K of them. Then we can also express this set in the following form, where we have binary variable lambda k which is 1 if we choose y bar k, and then we can of course only choose one of them. So then this is an equivalent expression. Next, we define an optimal cost for each point k, which we denote by f bar k, which we can obtain by solving subproblem with the corresponding objective function f. Now with all these, we can now reformulate the original problem, which was this, by using this expression for my feasible set for y and the corresponding optimal cost from here. Then this is a reformulation that we get, which we call the master problem. And you can see this master problem is an MILP, which we can solve using branch and bound. Of course, the problem here is that the cardinality of this set script k here can be huge, because it scales with or increases exponentially with the dimensionality of y, right? So then what we can do is we can apply branch and price, which essentially means that we apply column generation to solve the LP relaxation at each node of the branch and bound tree. And this is how we propose to solve the problem. In this case, this is how the column generation will work. So let's say we want to solve the LP relaxation of the master problem, which we denote by MP bar. So this would essentially be the root node of our problem. And so here you can see that integrality constraints on lambda, they're relaxed. Of course, the set is too large. So instead we solve a restricted master problem where we replace the set k with k hat, which is smaller, but which we will populate with more promising columns as the algorithm proceeds. And the way we generate new columns by solving this pricing problem, which is essentially the subproblem, but with a modified objective function. Now we minimize the reduced cost zeta, which is formulated using dual information from the master or the restricted master problem. So here the variables pi and mu are dual variables for the corresponding constraints. So we solve this problem. If we obtain a negative reduced cost, then we add the corresponding solution as a new column to the set. Now, at each iteration, we can obtain a bounds on the optimal value of MP bar. And so, of course, this RMP bar is a restriction of MP bar. So every solution of this will be an upper bound for MP bar. And then that solution plus zeta plus a reduced cost will give us a lower bound. The nice thing here is that if we solve the pricing problem with a global MINLP solver, then that will also provide rigorous bounds on zeta without solving to optimality. So without solving to optimality, you can still obtain valid bounds that drives the algorithm, and maybe only in the end we need to solve it to optimality to prove convergence. So as I said before, combine column generation with branch and bound, and what we get is branch and price. So here I will show the entire algorithm. We start by initializing the set of nodes with the root node. Then in the first iteration at the root node, we'll have initial column set. We'll then solve RMP bar at that node, at that root node. Then we solve the pricing problem. We obtain negative reduced cost. We add that column and then go through this loop again. So this is essentially my column generation algorithm. I stop once my reduced cost is 0. And then I check if that solution is integer feasible. If yes, then I solve the problem already at the root node and I'm done. Remarkably, this actually happens a lot in practice. But if not, I can obtain or easily obtain an integer feasible solution by solving the restricted master problem. So note this restricted master RMP is the master problem using a restricted set of columns, but now still with the integrality constraint on lambda. So by solving this, I get an upper bound on my master problem that I can use to check for convergence. If the optimality gap is small enough, I stop. Otherwise, I have to start branching. Now here I just say apply branching rules. I won't talk about branching rules that we applied. This is very application specific. It's not really the focus of this talk. But this is how you would go through this branch and price algorithm. And that's essentially all there is. It looks like a standard branch and price algorithm. If you're familiar with it, you probably have done this before. Maybe the only difference is that now, and that's the crux of this whole algorithm, is that now the pricing problem here is actually non-convex mixed integer nonlinear program, but one that we can solve efficiently. Now, next, for the rest of the talk, I will just go through a couple of examples where I show computational results, and the main goal here is to show that this actually has wide applicability. So this special class of MINLPs that we consider is actually not something that that we see only rarely. So in this example one, we consider a problem where we want to cut a set of circles from a given set of rectangles such that the trim loss is minimized. And here, the complicating constraints are assignment constraints, where we have a binary variable xr, which is 1 if we choose rectangle r, and then another binary variable yjr, which is 1 if we choose to cut circle j from rectangle r. So these are assignment constraints that are complicating. And if we remove them, then we have pricing problems that decompose into one subproblem for each rectangle R. This looks like a very specific problem, but is actually representative for a much broader class of problems, essentially a class of assignment problems. So we have these kind of complicating assignment constraints anytime we have to assign a set of discrete resources to discrete tasks. Now we solve different instances of this problem by varying the number of circles and number of rectangles. So here, the subproblems become harder if we increase the number of circles, and the number of subproblems becomes larger with the number of rectangles. We considered 25 instances, and each instance we compare the performance of the proposed branch and price algorithm, where we use Baron to solve the pricing problems, and with directly solving the full space original problem with Baron. And these are distinguished by there's a circle and square markers here. And for each case, we either show the wall clock time in this bottom plot, if it's solved to optimality within the time limit of 10,000 seconds. If it didn't solve to optimality, we'll show the relative gap that was reached at 10,000 seconds in this top plot. And also you can see that some of these markers here, they're empty or hollow. That means that not even a feasible solution was found. And this actually happens a lot for the full space model. We also organized the 25 instances into 5 blocks. So they differ in the number of circles. So for this block, we'll have 6 circles and 7 and so on all the way up to 10. And within each block, these instances, they differ in the number of rectangles. So that increases from left to right. So overall, the model size increases from left to right. So what we can see here, first thing is that the full space model doesn't really work. So it times out for all instances, and even for most of them, it didn't even find a feasible solution. Whereas the branch and price algorithm seems to work pretty well for most of them. Most of them is solved to optimality, and even for those that didn't solve to optimality, for most of them, they got pretty good optimality gaps. In the second example, we consider a multi-period capacity planning problem, where the discrete decisions are which units to install in which time period. So in this problem, we have orders that are processed in this production queue, and there's a chance of congestion. And so that is incorporated in the model by using chance constraints, which then lead to the nonlinearity in the model. Here we have these competing constraints. We have this variable xkt, which is 1 if, so this is a binary variable. This is 1 if unit k is installed in time period t. So the sum here from t prime from 1 to t essentially tells me if a unit k is available in time period t. If it is, then z can be non-zero, which is the amount of product j that we produce. Now, this isn't the structure that we need because the z variables are variables that will appear in the subproblems. They're continuous, and they're also in the complicating variables. So in this case, we can't directly apply our branch and price algorithm, but we can fix this by using a simple reformulation, where we just introduce a new variable ykt, which is defined as the sum here on the right. And then we just replace it with ykt, and then the y variables become the complicating variables, and they are discrete. So then our branch and price algorithm will apply. Again, we generate different instances. We generated from different numbers of units and different number of products, and within each block here, different number of time periods. So the pricing problem decomposes by time periods. And here, the difference between the two solution strategies is even more striking. The full space problem, I mean, we couldn't solve any of them. You couldn't even find a feasible solution for any of them, whereas the branch and price performs well on across the board. One other thing I want to mention is that in all the instances, no branching was required in the branch and price algorithm. So all the problems were solved at the root node. And this is also what happened in the next two examples. So this is what I mentioned before, that often we actually solve the problem at the root node already. Example 3, we'll consider the design of integrated water networks under uncertainty. So this is formulated as a two-stage stochastic program. We have non-convexities here that arise because of nonlinear terms. And the decisions here are which units to install in this network. Because it's a two-stage stochastic program, we can just apply standard reformulation using non-anticipativity constraints, which then become our complicating constraints. So in this case, the first stage decisions are they're binary. So y, I, v, s here is a binary variable that is 1 if unit I with size v is installed in scenario s. And then here you can see the set P here is my set of indistinguishable scenarios. So in this case, this pricing problem will decompose by scenario. Again, different instances here. Now 20 of them where we vary the number of different sizes that we consider for each unit and the number of scenarios within each block here. And we can see again, branch and price outperforms the full space model, but here also it starts to struggle in the larger instances. And that's mainly because the subproblems become harder to solve. Now in the last example, this is again a two-stage optimization problem. Here consider the design of multi-product batch plans that have multiple stages, and here demands are uncertain as well as some processing unit parameters. And we have nonlinearity here because we have a cycle time constraint that's nonlinear. Similar as in example 3, we have the non-anticipated constraints that are complicating. So the first stage is design variables. They're integer in this case. So they are the number of units that we install for each stage j. So then in our instances that we considered, we considered different number of stages. And this actually had a big impact on the performance and different number of scenarios. So we can see that for the smaller instances, branch and price still perform well. But then for the larger instances, it's comparable or even worse than the full space model. The main reason is because of the following. So in such a problem, we price out new columns from each scenario. But for those columns to be feasible in the master problem, it has to be feasible for every scenario. So sometimes or often in this case, we price out scenarios, we'll price out columns that are feasible for one scenario, but not feasible for all scenarios. And this is more likely in the cases when the number of stages is larger. So that's why we see that it doesn't perform as well in those cases. So this would be one example where it's not as performant. Now, let me just conclude. In this work, we attempted to combine the strength of global MILP solvers with the branch and price framework to solve large non-convex mixed integer nonlinear programs. We showed that the proposed branch and price algorithm is valid in the sense that it solves the given class of MINLPs exactly. I hope that it also was able to show that it's widely applicable because many relevant problems actually exhibit this required structure. And then finally, we also showed that it's effective through the computational results that show that the algorithm is very efficient in a lot of the instances that we considered. So with that, thanks for watching. I look forward to the discussion at the workshop, or just shoot me an email, contact me if you have any other questions. Thank you.